Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I am the social media manager at the Space Telescope Science Institute, and today we have a really cool topic to discuss with you on finding another citizen science initiative called This Detective, which we're going to talk about and was just launched today, right, John?
That's correct. Today.
Okay, so with me is you guys remember him, Dr. Ian O'Neill from Discovery News. Hi, Ian. Thank you for joining me, and he's going to help me with the discussion today and finding out more of the Space Telescope Science Institute. And we are going to be talking about a new citizen science initiative called This Detective. And with me today is the PIs and the people involved. Let me start from my right and going to left. Dr. Mark Kushner from NASA Goddard. Hi, Mark.
Hi, Tony.
Hi, and you're the PI, right?
Yeah.
Okay, great. So he'll be talking a lot about the project itself and where it originated from. Also with me is Dr. John Debus from the Space Telescope Science Institute. He's an astronomer here. Hi, John. It's good to see you again.
Hey, Tony.
We did another hangout a while back that I thought was really awesome, also on exoplanets and planetary disks. So welcome back. And Laura White, Dr. Laura White from the Zooniverse and Adler Planetarium. She is involved with the project from the Zooniverse perspective. So welcome back, Laura. It's good to see you again.
Thanks, Tony.
Okay, so let's go ahead and get started. So protoplanetary disks. That's the topic, or that's the science that we're working on here. John and Mark, you guys are heavily into this. Why don't you describe a little bit about what this research involves? What are you guys doing all day long? Let's start with
all
Mark.
day long. You check our email.
Well, you're not checking email and turning off windows that are feeding back YouTube videos. What else are you doing? Hello?
Well, I guess I'll start.
Yeah, go ahead. That's what. Yeah.
I study disks and the planets that live in them, and I try to understand how planets form, where planets form, why planets form, and whether there are any planets out there that can support life.
And how long have you been doing this? This sounds to me like an area of research that's pretty new. Is this am I right, or is this something that's been going on for quite a while?
It is. The very first planets were discovered in the 90s, and those discoveries just thing on its head. But it's been really exciting to be part of this growing field.
And John, this is not the only thing you study, right? You also do other things as well, if I'm not mistaken. But this is one of your main areas of research, correct?
Oh, yeah. Yeah, so I really like looking at dust around different things. So I think the last time we talked about dust around dead stars, and this is more dust around baby stars. And here at the Institute, it's a really great place to work on looking at debris disks. So you were talking about protoplanetary disks, and that's where planets start forming. And then after all the giant planets have formed, we often see these big dusty disks that have sort of lived on beyond giant planet formation. They don't have a lot of gas, but they have tons of dust, and they tend to have pretty interesting shapes and structures in them. So Mark also does a lot of work with these kinds of disks too. So I like taking pictures of them and seeing in sort of very fine detail what these disks look like.
So there's a distinction then between, I said protoplanetary disks. That is a stage that's a little bit earlier than what we're discussing here then. This is debris disks, which are a little bit after the major planets had formed and what's left behind.
Well, the nice thing about this project is we'll see both the really young ones and the older ones too.
Okay, all right, great. So is there any sort of preference to how you begin looking for these kinds of things? Like if I have a telescope, let's say the Hubble Space Telescope, or you just got through talking about going to Keck, where do you look for these things? How do you even start? Let's go with you, John.
Oh, okay. So I'm sure Mark was about to say the same thing, but actually back in the mid-'80s, there was the satellite called IRAS, which was an all-sky infrared survey. And that was really one of the first ways that people found evidence for these kinds of disks, at least like debris disks, because they saw that some stars that looked pretty normal at shorter wavelengths were way much brighter in the mid-infrared wavelengths. And they attributed this to dust, and when people started looking at these stars with the Hubble Space Telescope and with other telescopes, they started seeing that these excesses were due to dust disks that you could actually resolve out. So the first thing you want to do is you want to look for disks that are too bright in the infrared wavelengths of light.
Okay, so that's a pretty important point then, because this without infrared telescopes, then this research probably wouldn't be possible either, and that's another reason why this is a pretty new field of study, because the infrared detectors are the kind of detectors that have enough resolution that might be able to resolve some of these disks are relatively new as well. I mean, they've been coming on, well, they've been making big strides since the 90s, but I think they came into their own in like early 2000, mid 2005. Infrared detectors of all different kinds became able to resolve these things. So they're pretty. That's another reason why I think this science is only just now getting started. Is that right?
Yeah, maybe Mark can talk more. Yeah.
Okay.
Yeah, building infrared detectors is a bit of voodoo.
I know.
Yeah.
Yeah.
I mean, there's some of them that where in order to tune the bandpass, you have to more or less literally put them inside a clamp, a vise, and just kind of squish them until they give you the right properties.
Yeah, and they were, at least when I was working with the ones that I did at the High Altitude Observatory, they were pretty. The failure rate of making them was pretty high, and it was a difficult thing to do. But anyway, the detectors are now sort of mature enough that these kinds of things can get done pretty well. So, do you guys use the Hubble Space Telescope very much for this, or is it what are the primary instruments for looking at these and finding these disks?
John?
Oh, yeah, sure. So, like I said, IRAS was sort of the first telescope to really start where you were starting to look for them and find them in large numbers. And then with Spitzer being launched sort of in the early 2000s, that was another really great telescope for finding these disks unresolved. You couldn't see the disk properties at all. You just knew that they had extra mid-infrared light. And then the next upgrade is sort of WISE, because that was an all-sky survey, just like IRAS was, but it was up 10 to 100 times more sensitive than IRAS was. So that's bringing in millions of new sources to look at. But then the idea is, once you find that these objects seem to have disks around them, you can follow them up with high contrast imaging, try to actually see the disks themselves, and that you can do either with Hubble or with some of the most advanced adaptive optics systems from the ground. And those are really your two options right now. But hopefully in a few years we'll also have the James Webb Space Telescope, which hopefully will also really clean up on resolving a lot of these disks and turning them into lots of pretty pictures.
That's true. There's a lot of things that I think we're looking forward to from JWST, but the couple of things I wanted to point out while John was talking is we should talk a little bit about what adaptive optics is. Adaptive optics is a thing that many ground-based observatories have to sort of compensate for the fact that they're underneath the Earth's atmosphere. They are these electronic systems that will generally shoot out an artificial light source like a laser or a guide to make an artificial star, and then and then look at the light from that, and then very fast they will correct and cancel out the effects of the atmosphere, and using all kinds of mirrors and little flexible servos and things like that to get the effects of the atmosphere out, because it severely restricts what you can actually resolve on the ground, what the atmosphere does when it's boiling and light is trying to travel through all of these cells of different densities and things like that. And when we say resolved, that means that we can actually pick out detail from it. If you just see a blob, then that's not a resolved object. If there's more detail in there, you want either a larger instrument or a larger mirror, something like that, to give you better detail, and that's what we mean by resolving these things. So, is there any? Let me ask you guys, and maybe Mark, you can speak to this. Is there any sense of the statistics? Well, first of all, you're looking in our galaxy, right? Or are you looking in other galaxies?
We're looking all over the sky, and the odds are best that we'll end up seeing things in our galaxy, but there's no special filter we have that prevents us from looking beyond our galaxy.
Well, it would be limited by resolving them, right? I mean, you can actually resolve disks in other galaxies?
No, none of the disks that we're searching for with Disk Detective are resolved.
Okay. So, okay, we'll get to that in just a minute, but are they in our galaxy?
The ones that we're searching for are in our galaxy.
Okay, good. And so that leads to my question. Are there any statistics that sort of point to how many stars do you expect in our galaxy to have these kind of debris disks around them? Roughly speaking, is there any sense of that, or is it too early is that what you're trying to find out with this?
That is one of the things we're trying to learn.
Okay.
But we have some ideas from previous searches, like the IRAS survey that John introduced. And that taught us that something like 5% of stars that are similar to the Sun have disks. So maybe 1 out of 20.
Oh, okay. All right. Well, I furiously closed all of my windows at the beginning of this thing, so I'd like to talk a little bit now about the Disk Detective itself. Who first of all, whose idea was it? Who came up with the idea?
Well, the idea goes back. We really have to start by thanking the folks who flew the WISE mission, Ned Wright and those folks for flying such an amazing survey. I mean,
that got repurposed, didn't it? The WISE was launched to do one thing, and now it was woken up again. Am I remembering right?
That's right. WISE completed its original mission and was repurposed as NEO-WISE to study asteroids. What's so great is that this mission can do all kinds of different science. It doesn't just observe disks. It's good at finding brown dwarfs, at studying asteroids, at studying planetary nebulae and galaxies and all kinds of stuff like that. It just so happens that John and I, when we were starting to work on this project together, Disk Detective, well, we love disks. So we built something that would help us find more of the disks that we love.
Okay, so correct me if I'm wrong. WISE stands for Wide Field Infrared Survey Explorer, right?
That's right.
Okay, so, and like you said, it's a wide field telescope. It looks in the infrared. You can see a lot of the sky at one time, and apparently you can take many, many images and get kind of deep with it. And so it had done its thing, and then they turned it off, and then you guys decided, or someone decided that, hey, well, there's a lot of good science that we can do with this. Let's turn it back on, and NEO-WISE was born. So yeah, so this initiative, this Disk Detective initiative, wouldn't be possible without WISE. So that's the data set you're using,
Without
correct?
A great instrument like WISE.
Yeah.
WISE detected 750 million sources all around the sky.
When you say sources, what does that mean? What do you mean?
Bright dots of some kind, whether they're galaxies or disks.
Bright infrared dots.
Or brown dwarfs, or who knows what, white dwarfs. Yeah.
Okay. Okay, so Ian says, Ian, go ahead. You got a couple questions? Go ahead.
Yeah, I was going to say, do you want to find that video? Because I can probably step in for a little bit here. But I've just had a few. I just had a few questions already. Because I met John. When did I meet you first in person? I mean, it's strange to say meet somebody in person when you're always speaking online, but we did actually physically meet. Oh, it was in LA, wasn't it?
Yeah, it was a AAS meeting, an American Astronomical Society meeting, maybe like 5 or 6 years ago.
2008. Yeah, you're right.
Yeah.
It was 2008. There was a lot of conferences around then. But one thing I found fascinating about your work, specifically back then, was that you were looking at white dwarf stars. I mean, that was your thing. And the thing that blew me away, because at the time I was a blogger, I was blogging for Universe Today. I found it fascinating that you were analyzing white dwarfs and saying, okay, this white dwarf has got a debris disk around it, and its atmosphere has been polluted by, I think it was heavier metals that suggested that there was, some form of planetary body or asteroids in orbit, and you were saying this is the future of our solar system, because ultimately our star, the sun, is going to die and it's going to turn into a white dwarf. So actually what we're looking at is the far future of our sun. And I find that fascinating. So how does that, I mean, obviously this carries over into this new project. How many of these stars do you hope to find that are perhaps future versions of our solar system, perhaps these, doomsday versions of what happens to our sun?
That's how I got into WISE, is using WISE to look for these dusty white dwarfs. But I actually think with Disk Detective, we may not find too many like that, because a lot of the white dwarfs are just way too faint to be detected in all of the WISE bands that we're looking at. So when we look at the Disk Detective website, you'll see that we're looking at all 4 of the different infrared channels that WISE was detecting stars and galaxies in. And white dwarfs, because they're so faint and so far away, typically you only catch them in a couple of the WISE channels. So the way we selected our sample of stars on Disk Detective was actually looking for things that had detections at all 4 wavelengths. So I don't actually know how many white dwarfs we would find in this one. Maybe not very many at all. Maybe we'll find some planetary nebulae or red giant stars that might be very dusty too, and those also would tell us something about the future of our sun, because maybe the dust that these red giant stars push off are enough to explain some of the things that we see around white dwarfs as well.
That's cool. Well, that's going to be my mission then, to try and find some white dwarfs for you.
Great.
No, it's a very cool little platform, because I had to play with it a couple of days ago, and it's very easy. I like the Zooniverse interface as well, and I think it's very cool. But how do you think like human factors will come into play with this? Because it's going to be, you're looking at an image and you're trying to find stars with disks around them. I know that previous projects in Zooniverse have looked at human influence, selection bias and stuff. How do you think that's going to affect your results?
Maybe Laura should talk. Maybe
I bet Laura would be a good question for Laura. Yeah,
yeah, for Laura. Yeah.
So all of the Zooniverse projects kind of work on the same, use the same method, and that is that we get multiple people to look at every object. So it actually doesn't matter if one person is better at doing these, we kind of average things out at the end, and there is kind of some data reduction that happens when a sort of final catalogue is being collected together. But generally speaking, it's just the power of averages, right? The more people you get to look at something, the more reliable the result is. So, and it really depends on the project, because so different projects we get different numbers of people to look at in each object, and we kind of tweak that as the project goes along, and we find out how good people are at a particular task.
Okay, so let's move on now. I was able to recall all of my windows that were up. Thank you, Ian, for giving me an opportunity to do that, as I was frantically closing them earlier. So I'm back up, and let's start introducing the Disk Detective website. Now I have a video that was made at Goddard, and I think what we talked about doing was I will show that on my screen share, but the audio won't be able to be heard. So Mark is going to make some comments over as I do that. So let me start my screen share, and I will get that video up here.
I've got the script in front of me, so I'm going to do a live reading of it.
Oh, wow. Okay, well, my screen share button has to work, or else nothing's going to happen. I'm pushing it.
Mark, I dare you to do it in a Will Shatner style.
Okay. Oh, come on. This is crazy.
The WISE mission imaged about half a billion stars.
Every button is working but the screen share now. This is one of those things where it just figures. John, could I ask you to pull up the URL that is in the chat box for the oh, actually, I will send you the URL. It's just right here. My screen share button seems to not want to work.
Okay.
So in there is a link to NASA. If you could click on that and pull up the video, I'd appreciate it.
Yes, I will do that.
Okay, and I will. And if you just hit the full screen on the video and then push play, that should do it.
Yes, except for some reason.
Is your screen share not working either?
No, I'll get there. It helps when your window has a scroll bar. Okay, so screen share first and then do full screen on the video?
Yeah.
All right. It's not working for me either.
Oh, great. Okay. Can anybody share their screen?
Yeah, I'll give it a go. I've got the video up. I'll see if I can share it now.
Thanks, Ian.
So technical problem. So if that's gonna. There it is. Thank goodness. Okay, good. So we see Ian's screen. Okay, go ahead and make it. If you can go ahead and hit the full screen and then push play, it should do it. Oh no! Just hit escape. It went away.
Hey, y'all! Why don't you all go to YouTube and watch this thing?
Yeah. Okay, go ahead, John. Or go ahead, Mark.
Start yapping.
Yeah, go ahead. Can you scroll down a little bit, Ian?
Yeah, was it working or did it freeze up?
Well, now we're looking at the upper left corner.
Okay, all right, I'll restart it. Right. Huh.
Okay, so we're having technology.
Yeah, this is kind of weird. Sorry, 1 second. I'll restart it. It keeps going. What can you see now? This is, yeah, it's not working. It started up and then it stopped.
Oh, great. Okay. Well, let's improvise. So let's go ahead and talk about what the video was going to say. So it's an introduction into Disk Detective and to the citizen science project you had started. So let's go ahead and start talking about that. What are you hoping to do with Disk Detective?
Sure.
Mark?
I'll a quick summary. So, as we were saying, a big quest of astronomers for the last few decades has been discovering exoplanets. One of the ways that we do this is we search for young stars that are surrounded by dust. Dust indicates protoplanetary disks and debris disks. Because those are the environments where planets form. That's the environment where the solar system forms. The WISE mission has just been this remarkable tool for finding disks. From 2010 to 2011, the WISE mission scanned the entire sky. And the images are just spectacular. I hope you've had a chance to see some of them. You know, these green and magenta clouds of gas and dust and young stars. But anyway, John and I are most interested in the disks. So we wanted to try to find all of the disks in the survey. And in 750 million objects, you know there are going to be disks everywhere. But here's the trick. When you see a source in the WISE category, it's hard to tell by a computer anyway whether it's likely to be a star with a disk or whether it's more likely to be a background galaxy or an active galactic nucleus or an asteroid or planetary nebula or even an image artifact. And what we learned looking at these things, what several scientists learned was that you have to check them all by eye. You would try to program computers to sort through the or 2 billion images, and you could only get so far. You just have to use the power of the human eye. So, with this in mind, we launched DiskDetective. And in DiskDetective, you see animated flipbooks of images from WISE, from the 2MASS Sky Survey, and from the digitized Palomar Sky Survey, and some images also from the Sloan survey. And you see flipbooks of these images in several wavelengths. And looking at those images, you're able to spot the background interlopers and the false positives, the objects we want to discard, in a sort of natural way. It's almost like spotting prey in a dense jungle, something that the human eye is very naturally tuned to. So what we're going to do is, with your help, once we find all of these new disks that we hope to find in the data, we're going to follow them up with the Hubble Space Telescope, the James Webb Space Telescope, with ground-based space telescopes. And these are going to be great targets to search for planets around, extrasolar planets. We'll learn more about how planet formation occurs, where it occurs. We hope to find new groups of young stars, and generally study how planetary systems evolve during the lifetime of the star. So we're looking forward to working with you.
Okay.
Getting some feedback, Tony.
I know.
That was a piece of whale song.
It was beautiful. So I just got one question with, I mean, a recent thing that's come up with some infrared studies of other stars is the detection of dust and cometary material. Are you hoping to find star systems like that, like the Fomalhaut system? Are you going to be able to see things like that? Anything with a debris disk, I suppose, isn't it?
Yeah, well, so one of our science team members, Debbie Paget, is part of the WISE science team, and they actually used WISE to look for debris disks around nearby stars that have their distances measured. And so it was a subset of all the different sources that WISE had detected, a very small subset, you know, when you think about 3/4 of a billion. But what they did is they did find maybe a few dozen really good candidate debris disk sources, and then they followed them up with the Hubble Space Telescope, and some of the targets that they looked at have disks around them that you actually can image very nicely, very much like Fomalhaut or Beta Pictoris, some of these really famous debris disks that have these beautiful images. So that's exactly what we're hoping to do, just sort of on a larger scale if possible.
Okay, so I have finally a screenshot up of the website, and so let's go ahead and start showing people what they need to do. So I don't have any kind of account with. Well, I do have an account with Zooniverse, but why don't you?
You don't need it. I don't think you need it.
Okay, so
yeah, just get started.
Okay, so I start classifying.
Mm-hmm. Right, so the first thing you'll see is a little tutorial that comes up and tries to walk you through the whole process in a very, hopefully, intuitive way. I mean, the Zooniverse people do a really great job with this. So, you know, when Mark and I and the other science team members were first designing this thing, you know, I had made a little PowerPoint slide of what we thought it would look like, and yeah, they did a much better design job than I ever could have done.
So the URL that I'm at is disdetective.org. Very simple to remember, and this is what you were presented with. I clicked on the Start Classifying button, and now this comes up. So it says,
right.
Using the interface, we find new debris disk stars by looking at flipbooks of images, and so click the play button to start one flipbook. So.
Right, yeah, so you'll see different images at different wavelengths from the 3 surveys that we're primarily using. So the first ones start in visible wavelengths, and then they go on to the near infrared, which is light that's just a bit redder than what our eyes can see, all the way to the WISE wavelengths, the WISE images, which are in the mid-infrared. So this is very red light. And the idea is that these are all stars that we think are brighter in the infrared than they are in the visible, but we need to weed out all the galaxies and the other stuff. So as you're flipping through, you'll see a couple of different, you might see just something that looks like a blob, right? So this one looks like a blob. It's just a different size blob in all these images because each of these surveys could resolve images better or worse. So 2MASS sort of had the best spatial resolution, followed by the visible with the POS images, and unfortunately WISE, even though it's a great telescope in a lot of ways, it has sort of blurry vision compared to the other surveys. So a star will look more blobby as you get to longer wavelengths. So this one we consider a pretty good candidate because it looks just like a single blob within that red circle. So if you continue through, it'll sort of tell you, I think, what to look for. If you click on the little continue button, Tony.
Okay, so yeah, on the bottom it also says what instrument was there and the wavelength that I'm looking.
Right, yeah, just to help you. And you can drag it along and look around if you want to take more time, for example.
For a star to have a debris disk, it should mostly be contained within the red circle. And this red circle it's always the same size?
Yeah, that's roughly the ability of the WISE telescope to separate things out at the longest wavelength.
Okay.
Because we're really relying on that longest, that reddest color to tell us whether there's dust around these stars or not. And so what we're doing is we're looking at the shorter wavelengths where we have more ability to resolve things out or to image things to see whether there are multiple objects within that circle or whether there's a galaxy that looks like a galaxy at shorter wavelengths but just looks like a blob at longer wavelengths. And so those are the kinds of things that we want to get rid of if we can.
Okay. And it said that now it's talking about a scrub bar now. You want to talk about that a little bit? Sometimes you'll need to look at individual frames.
So Tony's now clicking on this thing. So if you want to have control looking at all the different wavelengths or going to a particular image, you can slide that around however you want to do it to really explore the images as much as possible.
Right, so here's a Digital Sky Survey 2 image. This one has 2MASS. WISE, there's a WISE image. And these are all of the same object.
Yep,
Okay.
That's the same object, just in different colors.
Okay. So as you go through the flipbook, you should pay attention to what survey each image is from. You'll be looking for different features and images for different surveys. For example, non-circular objects and images from the DSS2 and 2MASS surveys is a sign that it's not a disk. Is that true here? Non-circular, is that circular? That looks circular to me.
These are pretty circular. Now, obviously, there's going to be imperfections. A lot of our users have already found weird things in the data, like satellite trails or asteroid trails. So you might find a couple weird things, but that's okay.
Weirder the better.
Yeah, exactly. Who knows what we'll find.
All right, so now you classify. After you watch the flipbook at least once, you can select a classification for the star. This is a good candidate since it is round and entirely contained within the circle. Go ahead and select none of the above / good candidate, then click Finish. None of the above or...
yeah, it's all the way down there. Yep.
Okay.
And then hit Finish. Yep.
now Mark gets notified.
Right, and you'll get a voicemail from Mark with that noise every time you do one. He's done it about 10,000 times already.
Oh, good. Well, instead of me getting you feedback from
Imposter.
Okay, so here we are onto another one here.
Right. Yeah. So you closed out the tutorial, but
sorry.
no, that's okay. Don't worry about it. You can always get it back if you want. But if you go up to the top, you see you have a couple of buttons up there that you can kind of play around with. They should tell you what they are. Yeah, there we go. Well, now, yeah, there you go. You got back to the tutorial. You can close that out. Okay. I think if you go to the one that looks like a book and click on that, yeah, that gives you different examples of all the different things that you might run across.
Good candidate. So you play this to get a good candidate.
Right. Yeah, and so people can look through and sort of get a feel for what they're looking for.
Okay.
And there are a lot of different,
This,
the mostly what you'll find are things like the galaxy, right, where they look very much like a galaxy at the shorter wavelengths, but when you get to the longer wavelengths, it looks more like a star. And those are the ones we really want to put in a different category.
okay, so we're looking for things that are round, stay inside the circle, and don't look like any of these things.
Right.
Okay.
You got it.
Okay.
Yep. And if you close that out, one other thing you can do, click on the little what looks like a
Infinity?
no, sorry, on the top there's a star and then there's a little like word bubble. So click on the word bubble. If you go there, that'll take you to the talk area. And if you have an account, I think you'll see more things there. But basically, if you find an unusual object, you can start a discussion about it or tag some things about it. And this is something that I think most of the Zooniverse sites have something similar to this. And it's really cool because this is where everyone gets to talk amongst themselves about these different objects and ask questions of both the scientists and the Zooniverse people.
Oh, so it's got a social aspect as well. This is pretty good.
Yep. I don't know if Laura wants to talk more about these kinds of things in relation to the other Zooniverse projects, but this is something that I think is really cool.
Yeah.
Yeah, I seem to have forgotten my.
Yeah, this is something that we realized was important during our very first project, Galaxy Zoo. It's kind of where the science that you don't expect to happen happens. I mean, all Zooniverse projects start with very kind of well-defined questions that need to be answered. But it's the serendipitous stuff that comes out of people actually getting together and talking about science that's really exciting.
Okay. That wasn't me. This time.
It's a blender.
Sorry, we've got someone doing some cleaning, but
I know. Let's bring it all in. This hangout's got it all, folks.
Yeah.
Okay, so apparently I had one for Galaxy Zoo, but I don't know if that transferred over into Zooniverse or not. So
yeah, no worries.
Yeah, it certainly should have done. So
okay,
it's
I've forgotten my password then.
Yeah, just at some point you might just want to hit reset your password, and they'll send you a link. That you
I'll do that. But I can't.
On Galaxy Zoo,
unfortunately, demonstrate the social aspect of it very well. But that is a really important part of these. And I don't know, Laura, do you remember? Of course, you remember. There was a discovery made by a woman using, I think it was one of the, I think it was Galaxy Zoo. I can't remember the exact one. But anyway, she contributed to a paper. Yanni, I think her name was.
Yeah, it was Hanny van Arkel.
Thank you.
And
yes,
it was Hanny's foreverb. It was an entirely new astronomical object that had never been discovered before, and she's been in, I think, more than one paper actually, and in fact at some point they even pointed the Hubble telescope at this object to do follow-up observations. So that's a superb example of the kind of exciting stuff that can happen when people get together and talk about the science that happens on Zooniverse projects.
So was that feature built into Galaxy Zoo at the time? Were they able to discuss this thing, or was this feature born out of discoveries like this, where people were seeing things in these Zooniverse products and not knowing what they were and wanting to be able to talk about it? Is that where that kind of came from?
So the original projects had forums, just kind of your standard forum tools attached to them, and I believe Galaxy Zoo and Moon Zoo were the first projects that had these forums. But it soon became apparent that the forums kind of became victims of their own success. People were using them so much, and so many threads were being created, and people were having to go in and reorganize threads. And we wanted to kind of create a system where you could create collections of interesting objects that you found, so that things that you favorite when you're doing observations could then make a collection that you could use and potentially share with other people, because another kind of great example of a serendipitous discovery were the green pea galaxies. So this was a new type of ultra compact galaxy that was discovered by volunteers on the Zooniverse, on the Galaxy Zoo forum, who kind of said, hey, what are all these little pea things that we keep seeing? And they made collections of them. And we realized that, that's what scientists do all the time. They collect together things that interest them, and that's a very kind of important feature. So we built this talk tool, this talk discussion tool that's attached to all our projects now, in an attempt to kind of make it easier for people to make collections of things and also to have discussions around individual objects. So, hey, I found this thing, it's really cool. Anyone else seen it? Anyone else got any thoughts about what it might be? Or, hey, I've made this collection of really cool things and now I want to talk about them.
I know this. I think it's one of the most exciting times to be. Not just. I've always called this the golden age of astronomy because of all the really great telescopes and science that's being done and discoveries that are being made. But this aspect of it, this ability for just the tools that are out there for ordinary the regular citizens to just who love this stuff but don't get a chance to do it every day or do it professionally can contribute in a real meaningful way. So this is a very exciting time. So let's go back a little. Let's go back to the website. So is there anything else we should be showing, John or Mark? Do you want me to?
Thing. So so there are all these great serendipitous discoveries made at Galaxy Zoo. I just want to point out that with Disk Detective, we guarantee you a serendipitous discovery.
Wow, guaranteed, huh?
If you don't get a Nobel Prize winning discovery with Disk Detective, I will personally refund your money.
Wow, that's amazing. So this one that I'm looking at right now, this looks like a good candidate to me.
Yeah, it looks good. Go back down. Yeah, I'd say that's good.
All right, so good candidate.
Winner.
Yeah. I expect my Nobel Prize. Okay.
I'm printing it now.
Okay, you're pretty good. Okay, so now I've got another one, and I noticed the finish button doesn't come up until I've gone all the way through it.
That's right. So
I have to look at every wavelength that you've got, every image for this object that you have before I can classify it.
Yep, no cheating.
This one looks good too.
Yeah, I would.
So I'm going to say good candidate. What are my choices here? Multiple objects in the red circle, extended beyond circle in WISE images, not round in DSS or 2MASS, object moves off the crosshairs, empty circle in WISE images. Okay, I haven't seen any of that yet. So I've found all kinds of stuff already. So I'm like totally getting you guys there. This is another one. So okay, and so how come you guys don't require people to log in and sign up? I was able to do all of this anonymously. Is that on purpose?
Absolutely, yeah. We wanted to keep the barrier to participation as low as humanly possible. So, ideally, we'd like you to give us your email so we can tell you about other projects that come up, and we can give you feedback and access to the talk discussion tool. But if you just want to come along and play around, we don't want to stop you from doing that.
Are these weighted in any way? So do you is like an anonymous person? Does his or her classification mean less than someone who isn't?
No, absolutely not. We are able to kind of do some analysis on the users who haven't logged in because we know their IP addresses. So we know that they were there, and we can kind of find out which classifications that they did. So the value from unlogged in users is as great as from logged in users.
Okay, so none of that. So John or Mark, what are you expecting in terms of turnout? What do you hope? How many classifications do you need for you to be able to get some reasonable science done here?
By the way, we're going to be discarding all of your classifications for me.
Oh, nice. Why? Because of the feedback? Oh, I knew I was going to pay for that.
We'll never know it's you.
That's
you didn't log in.
How are you going to know? You probably probably look for the feedback person, I guess. I don't know. But yeah, so how many observations or classifications do you need before you guys are ready to start looking at writing some papers?
we've got 500,000 objects in our first list that we'd like help.
So you have a 500,000 objects. Presumably you want more than one classification for each one, so you're looking into the millions of classifications if you can get it. Right? Okay. All right. Well, I hope I can. I want to turn my
Space Corps. Laura, correct me if I'm wrong. Zooniverse project called Space Warps had how many millions of classifications?
Whoop. You're muted.
I think you're muted.
I think Space Warps has had a little over 8 million classifications. So then we shut the project down because they didn't need any more than 8 million. They kind of got the results they needed. So I mean, millions of classifications is not unusual for our projects.
We're lucky that people are interested in astronomy.
Yeah, we really are.
Well, that's true.
We couldn't do it without them.
Yeah, we really are lucky in terms of the field we work in. It's so easy to get the public engaged because this subject matter just comes naturally to us. Whether it's exoplanets or very distant galaxies, high redshift galaxies, protoplanetary disks, debris disks, like what you guys are talking about. Anything. It's just the idea that we're able to look at other stars within our galaxy and do things that we haven't ever been able to really do before and learn so much. It's easy to get people engaged. It really is amazing that we're lucky to be part of a field of study where that's the case. Hans Milling from YouTube is saying that the Spotter's Guide does not work in Google Chrome. No videos are shown, just the play button and descriptions. So thought I'd point that out. That's one.
Thank you, Hans.
Yeah.
We'll get someone to look at that.
Yeah, so I'll definitely look at that. Is there any, Ian, do you have any other questions you'd like to ask?
Yeah, I just have one question, and I don't know if this is a possibility, but because of course the other Zooniverse project, Planet Hunters, is there any plans to do a crossover with Disk Hunters? Because there's kind of a natural, organic relationship there. I'm just wondering if you can, pick out candidate stars and relate them to a planetary search as well as the disk hunting search.
Ian, yes. The Planet Hunters, as it exists now, is about studying stars that were observed with Kepler. And the Kepler field overlaps with the whole sky, of course, and we're studying the whole sky. So yes, we'll be studying that whole field.
Cool.
Wait, that was the good news. The bad news is that others have already done it to some degree. This Kepler field has been studied to death, really, by astronomers. So I'm not sure we'll have anything new to add for this version of Planet Hunters. Future versions of Planet Hunters, I think, are going to involve other data sets. And we're going to know about debris disks and protoplanetary disks everywhere in the sky. So whatever other data they have, we'll probably have some information.
Yeah, and one thing I'll add is that so right now Kepler its future is a little uncertain because it lost all of its reaction wheels and it can't do the kind of precise science that it was doing before. But the Kepler team is actually proposing for an extension to the mission that's slightly different, where it'll be slowly, it'll be checking some fields that are along the solar system ecliptic, because they've come up with this brilliant way of still getting really good photometry by, I think, aligning to the sun's magnetic field or the solar wind or something like that. I don't know the details, but it's a really great idea. So I could imagine a time where if that mission goes ahead, they'll have all this great Kepler-style data for different patches of sky, and hopefully by then, Disk Detective will have told them where all the cool debris disks are, and maybe there'll be some way to overlap those two projects together in an interesting way. So
cool.
We'll see.
So
no
cool.
Promises. I won't give you your money back if it doesn't happen, but.
If nothing else, I'm totally going to see about planning some kind of outreach session here at the Adler using both projects.
Great.
Yeah.
Nice.
So the Adler is I haven't been to the Adler in years, and do you guys have it? What are some of the outreach things you guys do there? Up
So
there?
we have a nice field trip program that we run here that uses we have orreries to kind of demonstrate to kids the transit method so that they can go away and use Planet Hunters. We're also working to kind of get more of our projects embedded on the museum floor. We're hoping not to just we think that the Zooniverse is a great thing for people to take home and do. We want to kind of have value-added experiences here at the Adler. So something that helps you better understand the science behind projects that you can then go home and do the project when you get there.
Right. Okay. Yeah. I remember the last time I was at the Adler, I think was in the '80s, that there was a American the planetary. It was a Planetarium Society meeting. Anyway, it was a beautiful place up there. I really enjoyed it.
Yeah, we have the best view in the city here.
Yes, definitely. Okay, so the website is discdetectives.org. It is a new citizen science initiative from the Zooniverse family of citizen science things. One of the last hangouts, a couple hangouts we did, was on the M83 project that Brad Whitmore has done. So I would encourage you guys to go there and start classifying. You saw how easy if I can do it, then anybody can do it, because as we can see, I can't seem to run a hangout without there being some technical issues, but this was a very easy website to use, so I encourage you guys to go and give it a shot. You can follow them at @disc_detective on Twitter. Is there anything else you want to shout out? Any other social things? You have a Facebook page?
We have a Facebook page. Yep.
Is it facebook.com/discdetective?
I don't know.
Okay,
I will
post
search this detective. Yeah.
I will post a link to that in the event and the description box on the YouTube video. Thank you guys for joining me. I want to thank Ian. Thank you for helping me and contributing. I really appreciate it. Dr. John Debus from the Space Telescope Science Institute. Thank you so much.
Thank you.
Dr. Laura White, thank you also for the Zooniverse, and Dr. Mark Kushner from Goddard. All of these guys have done some great work, and we hope that you will help them out and start doing some classifications on debris disks for them. It's a very interesting idea and a really, I think, a good opportunity for all of you guys to get involved. I want to apologize for some of the technical issues we had this time around. I will correct some of that in the editing after the fact, but I think
it just enriches the hangout experience.
Either that
makes it more authentic. Tony.
Fingernails on the chalkboard with that feedback there. So. Anyway, thank you all for your patience, and thank you guys for watching. And as always, keep looking up. Windows that are feeding back YouTube videos. What else are you doing? Hello?
Well, I guess I'll start.
Yeah, go ahead. That's what, yeah.
I study disks and the planets that live in them. And I try to understand how planets form, where planets form, why planets form, and whether there are any planets out there that can support life.
And how long have you been doing this? This sounds to me like an area of research that's pretty new. Is this am I right, or is this something that's been going on for quite a while?
It is. The very first planets were discovered in the 90s, and those discoveries just came on its head. But it's been really exciting to be part of this growing field.
And John, this is not the only thing you study, right? You also do other things as well, if I'm not mistaken. But this is when planets had formed and what's left behind.
Well, the nice thing about this project is we'll see both the really young ones and the older ones too.
Okay, all right, great. So, is there any sort of preference to how you begin looking for these kinds of things? Like, if I have a telescope, let's say the Hubble Space Telescope, or you just got through talking about going to Keck, where do you look for these things? How do you even start? Let's go with you, John.
Oh, okay. So I'm sure Mark was about to say the same thing, but actually, back in the mid-'80s, there was the satellite called IRAS, which was an all-sky infrared survey, and that was really one of the first ways that people found evidence for these kinds of disks, at least like debris disks, because they saw that some stars that looked pretty normal at shorter wavelengths were way much brighter in the mid-infrared wavelengths. And they attributed this to dust, and when people started looking at these...
the project itself and where it originated from. Also with me is Dr. John Debus from the Space Telescope Science Institute. He's an astronomer here. Hi, John. It's good to see you again.
Hey, Tony.
We did another hangout a while back that I thought was really awesome, also on exoplanets and planetary disks. So welcome back. And Laura White, Dr. Laura White from the Zooniverse and Adler Planetarium. She is involved with the project from the Zooniverse perspective. So welcome back, Laura. It's good to see you again.
Thanks, Tony.
Okay, so let's go ahead and get started. So protoplanetary disks, that's the topic, or that's the science that we're working on here. John and Mark, you guys are heavily into this. Why don't you describe a little bit about what this research involves? What are you guys doing all day long? Let's start with
all day
Mark.
long. You check our email.
Well, you're not checking email and turning off. Hello, everybody, and welcome to our latest Hubble Hangout. My name is Tony Darnell. I am the social media manager at the Space Telescope Science Institute, and today we have a really cool topic to discuss with you on finding another citizen science initiative called Disk Detective, which we're going to talk about, and was just launched today, right, John?
That's correct. Today.
Okay, so with me is you guys remember him, Dr. Ian O'Neill from Discovery News. Hi, Ian. Thank you for joining me, and he's going to help me with the discussion today and finding out more about the Space Telescope Science Institute. And we are going to be talking about a new citizen science initiative called Disk Detective. And with me today is the PIs and the people involved. Let me start from my right and going to left. Dr. Mark Kushner from NASA Goddard. Hi, Mark.
Hi, Tony.
Hi, and you're the PI, right?
Yeah.
Okay, great. So he'll be talking a lot about one of your main areas of research, correct?
Oh yeah, yeah. So I really like looking at dust around different things. So I think the last time we talked about dust around dead stars, and this is more dust around baby stars. And here at the Institute, it's a really great place to work on looking at debris disks. So you were talking about protoplanetary disks, and that's where planets start forming. And then after all the giant planets have formed, we often see these big dusty disks that have sort of lived on beyond giant planet formation. They don't have a lot of gas, but they have tons of dust, and they tend to have pretty interesting shapes and structures in them. So Mark also does a lot of work with these kinds of disks too. So I like taking pictures of them and seeing in sort of very fine detail what these disks look like.
So there's a distinction then between, I said protoplanetary disks, that is a stage that's a little bit earlier than what we're discussing here then. This is
right.
Debris disks, which are a little bit after the major